right, so we are going to talk about tides. This is a photo taken up in near the Bay of Fundy in Canada, I believe. High tide on the left, low tide on the right. So if you've ever been to the shore, to the beach, or even in downtown Boston, sometimes you notice the water level is higher than others, and that is because of the tides largely. So let's talk about what causes them. So we have to go out into space to look at the geometry of where the Earth is in reference to the moon. And what this diagram is showing you is that the gravity of the moon is pulling on Earth's oceans, and that fundamentally is what's causing the tides. So I'm calling this Tides Basics because at the end of the video, we're going to go into a little bit more depth. For those of you who are interested, I'll let you know when we get to the point where you could choose to stop if you didn't want to get into the weeds of the details. So Tides Basics. Tides are caused by gravity. The pull of the moon's gravity literally is pulling on our oceans and causing them to stretch out towards the moon a little bit. And we call this a tidal bulge. So the moon's gravity pulls ocean's water away from Earth's surface, creating a tidal bulge. And it turns out that this bulge happens not only on the side of the Earth that's facing the moon, but there is a bulge that happens on the opposite side of the planet as well. And this is the bit that we'll discuss at the end of the video if you care to stay on. Okay, so there are about 2 high tides and 2 low tides every day. So if you are standing in one spot on Earth on the coast somewhere, the tide will come in twice and it will go out twice. And this is because the Earth is spinning on its axis, and it does that once every 24 hours. So because the tidal bulge is a liquid and the Earth is a solid, the tidal bulge remains pulled in the direction of the moon's gravity force while the Earth is spinning. So you could sort of think about it as the Earth spinning within like a bubble of the ocean water. To visualize this a little better, though, I find it's easier if we stop the spin of the Earth, like going back to this animation here. It's sort of hard to visualize why does that mean too high and too low every day. So let's stop the spin of the Earth, because from our perspective, we don't feel like we're spinning, right? So I put our little stick figure person here to represent a place on the Earth. And right now that person is standing in a place where the tides are low. So if we go forward in time, as the moon orbits the Earth, so now instead of the Earth spinning, I'm having the moon do the spinning. And you can see that as the moon changes position, the bulge of the tide goes with it. And the moon is just off the screen here at the top. So here we are, our person is experiencing the first high tide of the 24-hour cycle, about 6 hours in. And as we keep going, the moon continues to orbit around the Earth. Now we are standing in the low tide position. Oh, and that should say low tide number 1. Sorry. No, that is low tide number 2. Sorry. Okay, continuing on. And again, our moon went off the screen to the bottom here. But now our guy at about 18 hours is experiencing the second low tide, and we are back to where we started 24 hours later. So again, 2 high tides and 2 low tides every day because the Earth is spinning within that tidal bulge bubble. Okay, but the moon isn't the only thing out there, right? The sun is out there, and the sun is very, 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 very large. So yes, the sun's gravity also pulls on our oceans and has an effect on the tides. So what I've done is I've just sort of exaggerated that tidal bulge and made it bigger. You can see to show the increased gravity. So now we're adding in the gravity of the sun, which is, you could think of it stretching out that tidal bulge even a little bit more, because now the force pulling on the water is greater. But the moon isn't always lined up directly with the sun like that. So what about the different moon phases? Now we've got the gravity of the moon pulling towards the top of the screen, while the gravity of the sun is pulling towards the right of the screen. So now we have to sort of play with, all right, which one's stronger, which one has more effect. And it turns out that even though the sun is so big in comparison with the moon, it's also really far away. And that we know that distance affects the strength of gravity. So more distance, the gravity gets weaker, and the sun is very far away. So it's the moon's gravity that is the stronger force on the oceans. So because the moon is so close in comparison, it has a bigger effect. So you can see what I did is I just switched the bulge now to face the moon. So the tidal bulge always faces the moon. Yeah, so sun is so far away, its pull is about half as strong as that of the moon. Now we've got a situation where the pull of the moon is not lining up with the pull of the sun. So they're acting against each other. And so, yes, the tidal bulge still follows the moon, but it's not as big any longer, because it's like it's getting pulled towards the moon, but it's also getting pulled towards the sun. So it becomes a little less extreme. So the high tides aren't as high and the low tides aren't as low. So basically it's just a less extreme tide, not as high, not as low. All right. These next two slides are where we sum all of this information up and make sure that you get it in your notes. So the situation where the moon and the sun are pulling in the same direction happens on two phases. It happens on the full moon, and it happens on, oh my gosh. I just realized I messed up this diagram. I moved the sun and now the phases are wrong. Okay, hold please. Okay, got it fixed. Now the phases are correct. So when the moon is in the new moon phase or the full moon phase, they line up with the sun. Everything's pulling in a straight line. So this is a situation called a spring tide. So new moon and full moon is when you get a spring tide. Sun and moon are pulling in the same direction. We get the biggest range, so that the force on the water is all working in the same direction. You get that really stretched out bulge, really high tides and really low tides, and new moon, full moon, as we said. The opposite situation is during the third quarter moon and the first quarter moon, when the moon's gravity is pulling in one direction, but the sun's gravity is pulling in the other. This is called a neap tide. So sun and moon pulling in different directions. The range of the tide levels is less. So it's not as high and not as low. And again, on the first quarter and third quarter moon. So pause the video and get all this into your notes. Okay, this is where you can stop if your brain is full. If you are still interested in going back to understand why do we get that opposite side bulge, stay tuned. Okay, so we are going to draw some force arrows here. And so the circle on the screen is Earth. The moon is to the right of the screen. And you can see the closer side of the Earth to the moon is going to experience a stronger force of gravity to the moon. So the water on this side has the biggest arrow pulling it towards the moon. The water on this side is also being pulled towards the moon, but less because it's farther away. And then this is a sort of a neutral spot in the middle of the Earth, just as a reference. So in the middle, this is what the force looks like. Let's look at the arrows to see how this works out visually. So in order to to think about this. We're going to sort of put ourselves in the middle of the earth where we put ourselves in the center of the frame of reference. So we're going to compare everything to us here in the middle. So that means that we're going to subtract out the force that's acting on us here in the middle just to make it 0. Okay, so basically we're trying to look at the situation from the point of view of being in the middle here where we don't experience any acceleration. So we do that by subtracting out the force arrow, the gravity force arrow. So if we do that here in the middle, we do it everywhere. And you can see I have the opposite arrows already added to all of our gravity arrows. And now the trick is to figure out what the net force is. And in the middle here, it's simple because they are equal and opposite. So in the middle, from our frame of reference here, we're experiencing no force. So we don't feel any motion. Out here on the side of the Earth closest to the moon, you can see that the net force is this much to the right. So that represents the oceans being pulled towards the towards the moon. On the opposite side, you can see when we subtract out our frame of reference that we're left with actually a net force that's a little bit to the left. And so this is why you get that opposite bulge, because the net force is actually pulling away from the moon. Now the rest of these, you can do the same trick, but it's an added layer because you can see they're not actually opposite any longer. And in high school, you'll learn about vectors and how they resolve, but the takeaway is that you're basically making a triangle, and so you can see the net force when you complete the triangle. And that's why these arrows that I'm drawing right now end up a little bit tilted, because it's a triangle. It's not just an equal and opposite situation. And on the top and bottom here, you can see that the net force is actually pulling the tides in towards the planet a little bit. Okay, so that was probably more than you were bargaining for, but in case you wanted to know, now you do.